Central America lies along an eastern segment of the seismically and volcanically active Circum-Pacific Ring of Fire. The North American plate moves west-southwest with respect to the Caribbean plate along the Motagua, Swan Island's left lateral transform plate boundary. On the west, the Cocos plate subducts beneath the Caribbean plate, producing hundreds of earthquakes every year and stunning volcanoes that loom over the region. Nearly 50 million people are concentrated along this fertile volcanic belt where, over the past century, transform faults and shallow intraplate earthquakes have had more human impact than have subduction zone earthquakes. To understand why, let's first examine earthquakes in the Cocos Caribbean subduction zone. Since 1970, there have been 13 major magnitude 7 earthquakes on or near the megathrust plate boundary, but there have been no great events of magnitude 8 or larger since 1900. In cross-section, we see that shallow earthquakes occur along and inland from the plate boundary, while deeper earthquakes occur only within the Cocos plate. Major earthquakes generally occur along the plate boundary at depths of 20 kilometers to 60 kilometers. Ground shaking is strongly controlled by distance of an earthquake from an observing location. A magnitude 7.4 earthquake occurring offshore at 20 kilometers depth will cause very strong shaking at the coast, but only light shaking along the volcanic arc where population centers are located. The same magnitude 7.4 earthquake occurring beneath the coast at 60 kilometers depth will also cause very strong shaking at the coast, but the intensity will decrease to moderate shaking along the populated volcanic arc. In 2001, a magnitude 7.7 earthquake occurred offshore of El Salvador. Extension in the upper part of the Cocos plate where it bends resulted in a normal fault rupture that propagated from 54 kilometers deep upward with maximum displacement of over 5 meters at about 35 kilometers depth. Strong to very strong ground shaking affected the rugged topography, inducing thousands of landslides that caused most of the 844 fatalities. In a typical tsunami-generating megathrust earthquake, rupture occurs at 3 to 4 kilometers per second, producing seismic waves and resulting ground motion with a range of frequencies, including short-period oscillations that people feel. This ground shaking is nature's warning to move quickly away from shore to high ground in anticipation of a tsunami. In 1972, Hiro Kanamori proposed the term tsunami earthquake for a megathrust earthquake that ruptures slowly and smoothly along the boundary at 1 to 1.5 kilometers per second, less than half the normal rupture velocity, so it radiates less energy in short-period seismic waves and more energy in longer period waves that people might not feel. On September 1, 1992, at about 7 p.m. local time, an earthquake off the coast of Nicaragua initiated at 45 kilometers depth on the subduction plate boundary. Some coastal residents felt weak ground shaking, but not strong and prolonged shaking that would have been taken as the natural tsunami warning. Within 30 minutes of the earthquake, a tsunami with run-ups reaching almost 10 meters struck the coast. Although initial earthquake magnitude based on short-period seismic waves was only a magnitude 6.8, subsequent analysis of broadband records revealed a maximum fault displacement of 4 meters and a moment magnitude of 7.7. This event confirmed Kanamori's tsunami earthquake hypothesis, and it motivates combining GPS and seismic observations to provide more accurate and rapid tsunami warnings. The Motagua Fault of Guatemala forms the on-land segment of the North American Caribbean transform plate boundary. At 3:03 a.m. local time on February 4, 1976, a major earthquake with moment magnitude of 7.5 initiated at 5 kilometers depth beneath the epicenter near Los Amates and ruptured 60 kilometers eastward and 170 kilometers westward along the Motagua Fault. The 230-kilometer ground rupture was the longest in the Western Hemisphere since the 1906 San Francisco earthquake. Along the rupture zone, very strong to violent ground motion was amplified in areas underlain by young volcanic ash deposits. offset of features such as chalk lines on soccer fields, rail lines, and roads verified left lateral displacement. Over 3 meters of offset on the fault occurred 30 kilometers northeast of Guatemala City. Earthquake-induced landslides occurred on steep valley walls, including within Guatemala City. The impact of the earthquake was staggering. Houses with adobe block walls collapsed on sleeping residents. This scene shows adobe houses reduced to rubble, while the steel reinforced concrete block school buildings with corrugated roofs were essentially undamaged. Widespread damage of transportation systems hampered recovery efforts. Normal fault displacement also occurred on the Mixco Fault in the western suburbs of Guatemala City. Basin and range-style crustal extension south of the Motagua Fault causes normal faulting that also poses local earthquake hazards. The Nicaragua Depression is a topographic valley along the volcanic arc through much of northern Central America. Detailed analysis of shallow subduction zone earthquakes and recent GPS observations indicate that a four-arc sliver of the Caribbean plate between the Middle America Trench and the volcanic arc is moving northwest, parallel to the trench at a rate of 1.4 centimeters per year. Shallow crustal earthquakes have resulted in disasters for population centers located along the Nicaragua Depression. Some strike-slip earthquakes along the volcanic arc have resulted from right lateral faulting on northwest-southeast-oriented strike-slip faults that accommodate northwest transport of the four-arc sliver. An example of this was the February 13, 2001 magnitude 6.6 event on the El Salvador Fault. 3 decades earlier and 360 kilometers southwest, a magnitude 6.2 earthquake struck just after midnight, rupturing the ground surface along faults that ran directly through central Managua. Ground displacements provide clear evidence for left lateral offset of multiple northeast-southwest-oriented strike-slip faults during this earthquake. The majority of wood frame and adobe or poorly reinforced masonry buildings were heavily damaged or destroyed by the 10 seconds of very strong to violent ground shaking. In a scene reminiscent of San Francisco in 1906, fires burned for days because firefighting equipment was destroyed in collapsed firehouses and roads were covered in rubble. For fear of epidemic disease, portions of the city were turned into mass graveyards. But how do the northeast-southwest-oriented left lateral strike-slip faults relate to the four-arc sliver? Let's examine textbooks tilting on a bookshelf. As the books tilt, the faults between the books are offset in a left lateral sense. In a similar fashion, left lateral strike-slip faulting between rotating crustal blocks in the Nicaragua Depression can accommodate coastwise transport of the four-arc sliver. While transform fault and shallow-crustal-intraplate earthquakes have dominated the recent history of deadly and destructive earthquakes in Central America, we should never underestimate the potential destructive power of subduction zone earthquakes. The Sumatra 2004 and Japan 2011 magnitude 9 earthquakes and resulting tsunamis delivered the lesson that many centuries may pass between great subduction zone earthquakes. We don't know whether or when a great magnitude 8 or 9 subduction zone earthquake may occur on the Cocos Caribbean plate boundary. What we do know is that Central America is one of the most vulnerable and highest risk areas in the world for earthquakes. Advancing emergency management and improving earthquake resilience of buildings and infrastructure are vitally important to minimize the impact of future earthquakes.